Hello everyone, this is Sarvesh. In this video, we'll be solving question 5 of 6 required for MAT104-Endsem. Okay, so in this question, we'll have to prove that Laplace transform of f dash t equals s times the Laplace transform of f of t minus f of 0. So let's start with what we do know about Laplace transform. We know that Laplace transform of any function f of t will be equal to the integral evaluated from 0 to infinity, the integral of e to the power negative s times t times a given function dt. Here there's a bit of constraint, s should be greater than 0, but that shouldn't affect too much. So let's try to solve the Laplace transform of f dash t with the same identity. So we'll be treating f dash t like any other function. So Laplace transform of f dash t would be equal to the integral from 0 to infinity e to the power negative s times t times a given function, that is f dash t dt. Now to further evaluate this integral, let's try to solve it by using paths. So this contains two different functions. Let me consider this one to be u and this one to be v. Now we do know how the integral by paths work. So any given function in the form of integral of u v dash will be equal to u times v minus, let's consider this to be v dash. Okay, so the integral by parts would be equating to u times v minus integral of u dash v. So we know u to be equal to e to the power negative st and v dash equal to f dash t. So u dash would be equal to the derivative of e to the power negative st, that would be negative s e to the power negative s times t. So the antiderivative v would be equal to the antiderivative of f dash t, that would be just f of t. Now just substituting these four values into this one, so our Laplace transform of a function f dash t would be equal to u times v. U times v is nothing but e to the power negative st times f of t, but we do have our limits of integral, so this would be evaluated from 0 to infinity minus the integral of u dash v. U dash is nothing but negative s e to the power negative st times v. V is again the antiderivative of v, it's nothing but f of t dt. Again the limits would be 0 to infinity. Now let's try to further simplify this. So e to the power negative st can be written as f of t over e to the power s times t. Again the limits are from 0 to infinity minus, no, see here negative s is a constant, so I am free to take this outside the integral. So negative s times negative is positive, so plus s times integral of 0 to infinity e to the power negative s times t f of t dt. Now this looks very familiar. This one is nothing but the Laplace transform of the antiderivative of the function we started out with. So I can substitute this entire part with just the Laplace transform of the antiderivative of a function, which would be f of t, and the remaining would be the same. So Laplace transform of f dash t would be equal to f of t over e to the power s times t evaluated from 0 to infinity. Now let's try to evaluate this limit. So t at infinity. T at infinity, let's try to evaluate it at t is equal to infinity. So f of infinity over e to the power s times infinity. Now we do know s is greater than 0 because that's the condition we started out with. So this one would be a very large number. F of infinity, no matter what number this one is, this entire one would tend to 0. So I can just equate that to 0 minus the function evaluated at 0 over, because 0 is the lower limit, e to the power s times 0. So again, s is a positive constant. So e to the power s times 0 is e to the power 0. E to the power 0 is 1. So f of 0 over 1. So that would be just, I can replace this by 1. So plus s times Laplace transform of the antiderivative of a function. So this would make our equation to be Laplace transform of f dash t is equal to negative f of 0 plus s times the Laplace transform of the antiderivative of a function. So just rearranging this would give us Laplace transform of f dash t would be equal to s times Laplace transform of the antiderivative of a function minus f of 0. And this is the one we need to prove. So like they always write, hence proved.